Hello?
Hello, sir.
Hello,
Hi.
sir.
Yeah. Um, what we'll do is we'll continue equilibrium.
Yeah,
So we had done till 13.4, 13.5 sort of, right?
yeah. Finished till 5.
So section 13.5 onwards. So section 13.5 is basically about using the equilibrium constant. Using the equilibrium constant. So in the previous section, he was talking about what is a heterogeneous equilibrium. Heterogeneous equilibria means some species have different states, like it
Yeah,
could
but
be some solid
mm,
or some liquid there as well in the
yeah,
reaction.
Yeah,
So he was discussing in the previous section that if you have a solid or a liquid, pure liquid or a pure solid, then you don't include it in the equilibrium expression,
mm,
right?
yeah,
Because the concentration of a pure liquid or pure solid
won't
remains
change.
constant,
Yeah,
right?
yeah,
So
yeah.
if we look at uh, 13.5, so one second, 13.5, he says, how do you judge the extent of a chemical reaction? We can judge that by the equilibrium constant. So he gives the example of 2H2 gas plus O2 gas
mm.
gives 2H2O liquid.
Even
So this,
gas only.
okay. In this one it is saying this is gas only.
Yeah,
So if this is the reaction, your K for this reaction is H2O square
square
by
H2 square.
H2 square and O2. You could also write this in terms of partial pressures.
Yeah,
You could write pressure H2O square by pressure H2 square and pressure O2.
mm,
That is your Kp.
yeah,
This is your Kc. There is a relation between them that is obvious. Kp is equal to Kc RT del N.
yeah,
Del N
Yeah,
is 2 minus 3 here.
yeah.
So Kp is equal to Kc by RT. Okay. Now, in this case, when you do the experiment and find out the equilibrium concentrations, it turns out that the equilibrium constant becomes very large. So 2.4 into 10 power 47.
Mm.
2.4 into 10 power 47.
47. Yeah,
That means that at equilibrium, the concentrations of H2O, this numerator is so much bigger than the
yeah,
denominator, right?
hardly anything.
So the concentration of H2O is much higher than the concentration of H2 and O2, right?
Yeah,
So that means that the forward reaction has almost entirely completed and
yeah,
very little of this is left. And
mm.
almost
yeah,
all
yeah,
of it is this, right?
Yeah,
So that tells you the extent of the reaction. So the higher the K for a reaction, the more the forward reaction goes to completion, right?
yeah,
yeah,
If you have a
yeah,
low value of your equilibrium constant, that means that the backward reaction, the forward reaction is not going. So the reaction does not happen much. So at equilibrium, almost entirely it will be reactants and not products that will be present if the value was low.
yeah, yeah,
So,
yeah,
so the first application basically of the equilibrium constant is to decide uh, what is the concentration, how much of the reaction has happened, right? If
yeah,
the reaction has an intermediate value of Kc, say a value in the range 10 power 3 to 10 power minus 3, 10 power minus 3 to 10 power 3, this is the Kc range, right?
yeah,
Then that means appreciable amounts of both are present. Like reactants as well as products are present in appreciable amounts. Like you can basically detect both of them, right?
yeah,
If you're if the ratio is much more than this or much lesser than this, then almost entirely
almost.
it is a completely forward reaction or completely reaction has not happened,
No,
right?
not happen. Yeah.
So
yeah,
that is one application. Then he talks about uh, so he's making these generalizations. He's saying if Kc is greater than root 10 power 3, products predominate over reactants. If Kc is very large, reaction proceeds nearly to completion. If Kc is
Hmm.
less than 10 power minus 3, product reactants predominate. Very small, then reaction proceeds hardly at all. If Kc is in the range, this appreciable concentrations of both are present, right?
Yeah.
Then predicting the direction of a reaction. Let's look at example 13.8. Okay. So 13.8. So let's see. Uh, Example 13.8. Uh, he's talking about a mixture of 1.757 mole of N2, 1.92 mole of H2, and 8.13 mole of NH3 is introduced into a 20-liter reaction vessel at 500 Kelvin. At this temperature, Kc is 1.7 into 10 square, right?
10
Is the
square, yeah.
reaction mixture at equilibrium? If not, what is the direction of the net reaction? Okay, so the reaction
Hmm.
basically is N2 plus 3H2 gives 2NH3, right?
Yeah.
And K at this temperature has K is a temperature dependent thing, okay?
Yeah, yeah.
Because the rate of the reaction is temperature dependent, right?
Hmm.
Yeah.
And K value is basically small kf by small kb, right?
Yeah, yeah.
So this is temperature dependent. So this is also temperature dependent. So he is specifying the temperature at which this K value has been mentioned. Now he's told us that what was taken 1.57 mole and N2 was how much? 1.92. H2 was 1.92 mole and NH3 was
Eight.
8.13.
Yeah, like 103.
These are the mole quantities. He has also told us the volume of the vessel.
Yeah,
So
so we get
by
the
20
concentration.
by 20 by 20 will be the concentration, right?
Yeah, yeah.
So K at this time, K expression, sometimes you K expression would have been what? K expression would have been NH3 square by N2 H2 cube, right?
Yeah, yeah.
So this K, in this K expression, you can only use concentrations at equilibrium, right?
Hmm. Hmm.
Yeah.
You cannot use concentrations at an arbitrary moment, right? So we
Yeah,
will
Yeah.
define
Yeah.
something called a reaction quotient, which is QC, which will be the same expression, but this is at any moment, right?
yeah.
I mean, at the starting moment also, they will have some concentrations like this and this and this, right?
Yeah, yeah.
Yeah.
So
Yeah.
QC gives us, it is the same expression as the equilibrium K expression. However, it tells us whether right now the reaction is at equilibrium or not, right?
Hmm.
So
Hmm.
this QC ratio, this is called reaction quotient. Reaction quotient, if we find right now, right, it will tell us, how will it tell us? Let's figure out. So this is going to be 8.13 by 20 whole square by whatever 1.57 by 20 multiplied by 1.92 by 20 whole cube, right? Correct.
Yeah, yeah.
So 20 square here and 20 to the power 4 here. So 20 to the power square will come here, right? And it is
Yeah,
8.13
yeah.
whole square by 1.57 into 1.92 whole cube. So I will almost say that this is almost 8, this is almost 64. 64, 8 by 1.5, right? Almost, approximately,
Yeah, yeah.
right? So
Yeah.
8 by
Yeah.
3 by 2, so 16 by 3, so almost 5.
Almost.
Almost 5 into 400, right?
Yeah.
So reaction quotient is almost 2000, right?
Yeah, yeah.
However, this was 1700, no?
Yeah, so it's
170.
not a
170 this was, no? K,
Hmm.
Yeah. Yeah.
right? K value should have been 170 at equilibrium, right?
Yeah.
But right now at the initial moment, the value of Q is 2000, right?
Yeah, yeah.
Yes. Yeah.
So initial moment, we are seeing that NH3 is much more than what is required at equilibrium, right?
Yeah,
Yes.
yeah.
The
Yeah.
numerator is bigger, like NH3 is more than what is necessary at equilibrium. So actually the backward reaction should happen, right?
Hmm. Hmm.
Yeah.
Yeah.
Backward reaction should happen more so that NH3 should reduce and the ratio
Reduce.
comes down
Yeah.
to 170, right?
Yeah.
So
Hmm.
basically what we are learning is that if you calculate your QC at any moment, if QC is greater than KC, then backward reaction is more fast.
Yeah.
Backward reaction has to happen faster because then only you will reduce it to Kc, right? And if Qc is less than Kc, then forward reaction is favored.
Yeah. Yeah.
Yeah.
And if Qc came out to be equal to Kc, then it is already at equilibrium.
Equilibrium. Yeah.
Is everyone understanding?
Yeah.
Yeah. Yeah.
It is already at equilibrium.
Hmm.
So basically, QC is like a exactly same expression as equilibrium constant. It's just telling us that when you start off, whether you are at equilibrium or whether you are already crossed the equilibrium and backward reaction has to happen, or whether you are before equilibrium and forward reaction has to happen.
Yeah. Yeah.
Right. So that is the point of this thing. Then uh, 13.8, 13.9, again similar question. You will be able to do it. Now calculating equilibrium concentration. So another application of the equilibrium constant is to figure out what is the equilibrium concentration going to be. So if you have your K is known, then you can write and some initial concentrations of reactants, then you can
Yeah.
figure out the remaining concentration of some product at equilibrium, right?
Yeah. Yeah.
That is straightforward. Again, you just put the thing in the formula, right?
Yeah.
And you will get the equilibrium concentrations. So
Okay.
for example, he has done this question. 13.9 we can see. Let's see 13.9. 13.9 says Kc for the reaction of H2 and I2 is 57 at 700 Kelvin. The reaction is this. Okay, H2 gas plus I2 gas is 2Hi. Kc is equal to 57
57.
at 700 Kelvin. And what he's saying is 1 mole of H2 is allowed to react with 1 mole of I2 in a 10-liter
10
reaction
liter.
vessel. What are the concentrations at equilibrium? What is the composition of the equilibrium mixture in moles? Okay,
Yeah.
fine. So 1 mole in 10 liters. So 0.1, 0.1, right? Molarity.
Yeah. Yeah.
This is the initial situation, right?
Yeah.
So what we will do is we will think about what will happen at equilibrium. At equilibrium, it should be right now initial is zero here, no?
Zero. Yeah.
So if you calculate QC at this moment, QC will be zero, right?
Yeah. Yeah.
Because that is HI square by H2I2.
Hmm.
So right now QC is zero, and
Zero. Yeah.
so it should be favoring the forward reaction right now
Yeah.
because eventually it has to become
Hmm.
57, right?
57. Yeah.
So forward reaction happens. So you can assume that amount this becomes like this, right?
Yeah.
And this should become 2x, right?
2x. Yeah.
Because some amount will be consumed and some amount will be formed, right? HI.
Yeah. Yeah.
If X moles are consumed, then 2x moles are formed.
Yeah.
And equal moles will be consumed here. So
Yeah.
therefore
Yeah.
this. So let's say this is at equilibrium. So then your K expression becomes 2x whole square by 0.1 minus x whole square, right?
Yeah. Yeah.
Okay. So you get 4x square by 0.1 minus x whole square.
Yeah.
Okay.
That
And
is
this should be equal to your
57. Yeah.
right. So there are multiple ways to do this, but one way that you should learn is this expression. Actually, in this case, you can just take square root. Okay.
Mm-hmm.
In this case, you can just take 2x by 0.1 minus x is equal to root 57, right?
Yeah. Yeah.
And
Hmm.
you can just solve it like that. 2x root 57 is going to be 7.5, almost 7.5
Yeah.
into 0.1 minus x, right? So this
Yeah.
is going to be 0.75 minus 7.5x,
Hmm.
and you'll get 9.5x is equal to
7.5.
0.75,
Yeah.
and x will be almost this. This is an approximate calculation, but this will be almost true. So 75 by 100, 95 by 10, and 15 by 19, and
Hmm.
3 by 2, and 3 by 38, right?
Yeah.
So
Yeah.
this becomes point 0.08.
0.078.
uh, 0.08, no, almost.
Yeah,
Yeah.
almost.
X is equal to almost 0.08, right?
Yeah.
So that is my approximate amounts that will be there. So this will be 0.16 molar, and this will be 0.02 and 0.02 almost, right?
Mm.
Maybe there is some
Yeah.
calculation mistakes, but mostly it should be close to this. So what is coming X for him?
He
Point
has
zero.
done for a negative 7.5 also.
He is done for negative, right?
Like he's done
Positive
for
will be.
positive and negative 7.5 when you're taking the root.
See, he is getting X is 0.079, no? So uh, equation with the positive square root of 57 gives this. Equation with negative square root gives this, right?
Yeah, but
Because
negative
the
is
initial
more than one
concentration
molar. Yeah.
of this are 0.1. Oh, okay, makes sense.
Yeah, yeah.
Because the initial concentration of H2 and IT was 0.1, X cannot exceed 0.1, right? Or
Yeah.
Yeah.
X X cannot exceed 0.1. So our answer is right, no? 0.079.
Yeah, that's correct.
Yeah, yeah. It's correct.
So our answer is more reasonable because it is less than 0.1, right?
Hmm.
You should
Yeah.
not get a root which will get a value of like which is
Hmm.
bigger than the initial amount, right?
Yeah,
So,
yeah.
so that is more or less correct only what we got, right? 0.2, 0.2 is
But
almost correct.
like, suppose we take negative root and get something that's less than 0.1 only. So will we have two answers then?
No, it cannot be. Ultimately, one of them has to be
Yeah,
unreasonable.
okay. Hmm. Yeah,
It cannot be two answers can come in a physical situation.
yeah.
This is an actual chemical reaction, so actually it will be only one concentration. There is, while mathematically solving, you might get multiple roots, but one of them has to be unreasonable,
Yeah, okay.
right? Something has to be wrong there, right?
Yeah.
So yeah, so this is fairly straightforward, but I wanted to actually point out something else which will probably be apparent in the next chapter and all. So sometimes what you can do is this expression, right? Sometimes what happens when the k value is very high or very low, right? Then you can
Hmm.
say that 0.1 minus x is almost same as 0.1 if the k value was very low.
Okay.
Okay.
Yeah.
So if k value was very low, basically forward reaction doesn't happen much, right?
Hmm. Yeah.
So this is almost same as 0.1. Then you can immediately solve by saying 4x square by 0.1 minus x is almost same as this. So 0.01 is equal to k, right?
Yeah.
Because
Yeah.
0.1 minus x is 0.1 only, and 0.01 it will become, right? And
Yeah,
you will
yeah.
get x from x square is equal to 0.01 k by 4, right?
Yeah.
And then you have to actually do a check. So whatever value of x comes from here, right?
Hmm. Hmm.
You have to check whether this assumption is true or not.
Yeah.
Like
Yeah.
x value should be negligible compared to 0.1.
Hmm.
Yeah.
Then only this assumption is true, correct?
Yeah. Yeah.
So this assumption will be true only if the k value was small. So if you take k is 10 power minus 6, let's say, right?
Yeah.
Then this becomes 10 power minus 8 by 4, right? So 10 power
Yeah.
minus
Yeah.
4 by 2, right? So 5 into 10 power minus 5, right?
Yeah.
So now you can say that 0.1 minus 5 into 10 power minus 5 is close to 0.1 only, right?
Yeah. Yeah.
So in that case, this assumption is true, and it makes sense to use that fact and go ahead and find the x value very easily by this, right?
Hmm. Hmm. Yeah.
However, if it was some high value of k here, no, 100 or something, right?
Yeah.
So then x is coming half, no, if k was 100.
Yeah. Yeah.
Then 0.1
Yeah,
minus
yeah.
half is not,
Not.
I mean, half is unreasonable, but
Hmm.
k value has to be something. But if it was comparable, then that assumption is unreasonable, right?
Yeah.
Yeah,
So
yeah.
then you will have to solve it by a regular way. Like you'll have to actually account for the x.
Yeah.
So in some questions, you will see that there. Oh, situations where you can sort of ignore the 0.1 minus x term and call it 0.1 only.
Mm-hmm. Okay.
But when you do that approximation, you have to also go back and check eventually that whether that assumption was true or not later,
Yeah, yeah.
right? So, okay, then this is fine. See, in the next question, there will be a quadratic that will come. Like you have to solve it properly, right?
Mm-hmm.
So you can try out these questions. These are not difficult. Now we go on to 13.6, which is factors that alter the composition, or basically Lee Chatelier's principle, or factors that change the composition of an equilibrium mixture. Does that change equilibrium mixture composition? So basically, we are going to try to learn how to modify the equilibrium mixture's composition by
Mm-hmm.
changing some things like changing temperature, volume, pressure, whatever, right?
Yeah, yeah.
So because ultimately we need to make our reactions productive for us, right? Like it's not like whatever the reaction is happening in nature, that is what we are going to stick with.
Yeah, yeah.
Some reactions in nature are not useful, or even if they are useful, they're not happening with substantial amount of concentration of the product. They're not happening
Yeah.
fast enough or something, right? You
Yeah,
want to
yeah.
modify that for your purposes.
Mm.
So how does that happen? How do you do that? So he's saying one of the main goals of chemical synthesis is to maximize the conversion of reactants to products while minimizing the expenditure of energy, right?
Mm-hmm. Yeah,
This objective is achieved easily if the reaction goes nearly to completion at mild temperature and pressure, right?
yeah, yeah,
If your reaction itself already is going to nearly to completion, then there is no problem, right?
yeah,
If the reaction gives an equilibrium mixture that is rich in reactants and poor in products, however, then the experimental conditions must be adjusted, right?
yeah, yeah.
So, for example, the Haber process ammonia synthesis, right? It is very important to produce ammonia because ammonia is useful in fertilizer manufacture.
Mm.
And that reaction, however, doesn't happen at a normal temperature and pressure to a substantial degree.
Yeah, yeah.
So several factors can be exploited to alter the composition. So what are the factors? So concentrations of reactions or products can be changed.
Mm.
So concentration of reactants or products can be changed. You can also change temperature, and you can also change pressure, right? These factors you can change, and pressure and volume are interchangeable.
Mm.
Pressure, volume also you can change. So he will look at all of these factors. A possible fourth factor, the addition of the catalyst, right?
Yeah,
Catalyst, however, will not change the reaction composition, mixture composition.
Yeah.
See, catalyst, what it does, it reduces the activation energy and makes the reaction faster, right?
faster. Yeah.
So making the reaction faster makes backward reaction also equally fast,
Mm-hmm.
Yeah.
Yeah.
right? So suppose this was the normal reaction, right?
Mm.
In the presence of a catalyst, it can become like this, right?
Mm. Mm.
And so this activation energy barrier has been lowered, right? This was
Yeah.
the activation energy barrier normally. In the presence of a catalyst, it is lowered. But normally, this was the backward reaction activation energy barrier, right? That is also lowered, no?
Yeah, yeah.
So catalyst increases, Kf is increased, but Kb is also increased, right?
Yeah.
And it is
Yeah.
changed by the same amount. Like it's the same one pathway that your new pathway that you are following. So both the reaction rates are speeded up by the same amount. So catalyst actually doesn't alter equilibrium composition. Why? Because
Mm-hmm.
capital K depends on the ratio of Kf by Kb, right?
Yeah, yeah.
So unless you can change your K, right, you cannot change the equilibrium concentration, right?
Yeah. That's,
If both are speeded up, the reaction will reach equilibrium faster.
mm.
Reaction reaches equilibrium faster. So the time taken to attain equilibrium
Yeah.
is reduced,
Reduced.
right?
Hmm.
So the presence of a catalyst can reduce the time taken to reach the equilibrium, but the equilibrium will still contain the same amount of reactants with respect to the products.
Yeah.
So that is not a factor that will be useful to us so much. Okay.
Hmm. Hmm.
It will only reduce the time taken to reach equilibrium.
Yeah.
So what we will look at is the first three factors where we are changing concentrations of reactants and products, changing temperature, and changing pressure and volume, right?
Mm-hmm.
So
Yeah.
the principle here is Lee Chatelier's principle, which says that uh, so this is a very important principle here. It says that if you change anything in the mixture, right? If you
Yeah.
change anything in the reaction mixture, any external change that you bring can be called like a stress, right? You have
Mm-hmm.
added something, you have increased the temperature, you have decreased the volume. All of those externally brought about changes can be called as a stress to the system, right?
Mm-hmm.
And
Yeah.
the reaction mixture will respond in such a way that it reduces the stress to the mixture. Okay.
Mm.
So
Yeah. Yeah.
basically, whatever you do, it's like an external stress that you are imposing on the reaction mixture, and the reaction mixture will react in such a way that it reduces the effect of that external stress. Okay.
Mm. Yeah. Yeah.
So what we will see is that this general principle is very applicable in terms of, like, suppose you added extra reactants to the mixture, right?
Yeah.
More reactants you put in, right? Then
Mm-hmm.
Mm.
obviously the reaction will proceed in a way that it reduces the extra stress. So what was the stress? Extra reactants, right?
Yeah.
So to
Yeah.
reduce that, I need to make the forward reaction go fast
Faster. Yeah.
so that the reactants are consumed also, right? Quickly.
Yeah.
Yeah.
Okay. So that is one way, and you can sort of see the underlying principle why that will work, because if you introduce more reactant concentration in the beginning, right,
Hmm.
then
Yeah.
forward reaction rate from the previous chapter, is kf into the reactant concentration, right?
Yeah.
That has increased, but backward
Increase.
reaction has not changed. No,
Yeah.
backward reaction rate has not changed at all.
Mm-hmm.
Mm.
Yeah.
So forward reaction will go faster now, right?
Yeah. Yeah.
So the equilibrium concentration will change slightly.
Change. Yeah.
Correct? Are you understanding that?
Yeah. Yeah.
Yeah.
So what will happen basically is equilibrium constant, that k value will be having product concentrations by equilibrium reactant concentrations, but you have changed the reactant concentrations, right?
Yeah. Yeah.
The equilibrium constant will be different now, right?
Yeah. Yeah.
Mm.
Similarly, if you increase the temperature of a system, right? If you increase temperature of a system, the system
Mm-hmm.
wants to behave in such a way that reduces that stress. So system wants to behave in a way to reduce the temperature, right?
Yeah. Yeah.
So how will it reduce the temperature? It will go in the direction which
Which
is
is
endothermic.
endothermic. Yeah.
Yeah.
It will go in the direction in which the reaction absorbs heat, right?
Yeah.
So that it absorbs the heat, so temperature is lowered, right?
Yeah.
If it went in the exothermic direction, it would have released heat and increased temperature further, right?
Yeah. Yeah.
You understand? So change
Yeah.
in
Yeah.
temperature will result in reaction going in the direction of endothermic direction, right?
Yeah.
So obviously, when you have learned thermochemistry, you realize that the reaction can be endothermic or exothermic in the forward or backward
Or
direction,
backward.
right?
Yeah.
Mm.
But that is
Yeah.
a thermodynamics thing that doesn't change because of whatever that is intrinsic to the reaction, right?
Yeah. Yeah.
That depends on internal energies, whether it is endothermic or enthalpies, it depends on, right?
Yeah.
So that is fixed. So if you increase the temperature of an endothermic reaction, right, it will go ahead in the forward direction faster, right? More of it will happen in the forward reaction.
Yeah. Yeah.
Yeah.
You understand?
Yeah. Yeah. Got it.
Similarly, changing the pressure and the volume also has similar effects. So if you increase the pressure, right? If
Mm.
my stress is increasing the pressure of the system, right?
Yeah.
Then again the reaction will proceed in a way to relieve the
Relief
stress,
stress. Yeah.
to lower pressure, right?
Yeah.
So
Yeah.
basically the reaction will proceed in a direction which has lower number
Yeah.
of moles of gas.
Yeah. Yeah.
So
Yeah. Yeah.
if you have more gases in the product side, the reaction will proceed in the backward direction, right?
Hmm. Hmm.
If you have more gases in the reactant side, reaction will proceed in the forward direction faster, right?
Yeah. Yeah.
So if you think about N2 plus 3H2, N2 plus 3H2 gives 2NH3, right?
Hmm.
All of them are gases. Then what will happen if I increase pressure on this system, right? If I increase
Yeah.
pressure here, then reactant will try to relieve the pressure by becoming less gas side. It will go towards the less gas
Yeah.
side.
Yeah.
Yeah.
That
Yeah.
is why this reaction is carried out at high pressure,
High
500
pressure.
atm and
Hmm.
all,
Okay.
so that more of the reaction is driven forward, right?
Yeah. Yeah.
Yeah.
Similarly, since pressure we understand, so changing volume does the same effect. Changing volume will also change the pressure, in because if you increase the volume, you are reducing the pressure, right? Sort of.
Yeah.
Hmm.
Or you are basically reducing the concentrations, right?
Yeah. Yeah.
So I mean you can just think of volume as the opposite of pressure, right? So increasing the volume reduces the pressure. So
Yeah.
if
Yeah.
you increase the volume of this reaction, it will go towards the side which increases pressure, right?
Hmm. Yeah. Yeah.
Understand? So it should go backward, reaction will be favored if you increase the volume, right?
Hmm.
For
Yeah.
the ammonia reaction, right?
Yeah. Yeah. Yeah.
Actually, this principle is quite general in the sense that there is a similar principle that you learn in physics also. In the chapter on EMI,
Hmm.
electromagnetic induction, there is something called Lenz's law. Okay. So, Lenz's law, if you have done in 10th standard, you would have done some motors and all, no? Induced
Yeah,
friction,
we
then some
had done what?
some stuff like current is induced and
Yeah.
those things you have done, no, a little bit.
Yeah. Yeah.
So in the
Yeah.
EMI chapter, we will see that there is a quantity called magnetic flux, and if you change the flux, right,
Hmm.
change the flux of a magnetic field through a closed loop, what will happen is current will flow in such a direction so as you can counter that change against that change. Okay, so if I increase the flux, current will go in such a way so that the flux can be reduced. If I decrease the flux, current will flow in such a way so that the flux is increased. So it is actually this exactly similar principle in physics also there. So
Hmm.
whatever
Yeah.
change you bring about to the system reacts in such a way so that it can counter that change,
Yeah. Yeah.
right? That is true even in EMI Lenz's law. So for now, we'll just focus on this now. Uh, okay, so net reaction, he's saying if a stress is applied to a reaction mixture at equilibrium, net reaction occurs in the direction that relieves the stress, right?
Yeah.
The word stress in this context means a change in concentration, pressure, volume, or temperature that disturbs the original equilibrium, right?
Hmm.
Reaction then occurs to change the composition of the mixture until a new state of equilibrium is reached, right?
Yeah. Yeah.
Yeah.
So 13.7, if you see, if you change the concentration of an equilibrium mixture. So right now
Hmm.
he's discussing changes in concentration.
Concentration. Yeah.
So so he's talking about that ammonia reaction only, and for the ammonia reaction, the Kc is 0.291 at 700 Kelvin, right?
Hmm. Yeah.
Yeah.
Suppose we have an equilibrium mixture of 0.5 molar N2, 3 molar H2, and 1.98 molar this, and that will disturb the equilibrium by increasing N2 concentration to 1.5 molar, right?
Yeah.
Hmm.
See, at equilibrium, the N2 was 0.5. Now you have tripled it, right?
Yeah. Yeah.
So reaction should go in the direction that brings the N2 down, okay,
Into down. Yeah.
which is the forward direction, right?
Forward. Hmm.
Yeah.
Reaction
Yeah.
will occur to relieve the stress of increased concentration of N2 by converting some of the N2 to NH3. As the N2 concentration decreases, H2 concentration must also decrease, right? Otherwise, how will
Hmm.
the N2 decrease, right?
Yeah.
yeah,
and NH3 must increase the in
Yeah. Yeah.
accordance
Yeah.
with the stoichiometry of the balanced equation, right?
mm,
Yeah.
So the changes are shown in this figure. That is fine. So normally it was initial equilibrium was H2, NH3, and N2 were fixed at these levels, right? See,
yeah, yeah,
there's a constant lines here, no? Because
Yeah.
initially the situation was at equilibrium, so concentration was constant, right?
Yeah. Yeah.
mm,
Now see, there is a sudden jump in the N2 level, right? It has become 1.5, right?
Yeah.
yeah,
Yeah.
yeah,
1.5 it has become up, so there is a vertical line, there is a sudden jump there. Now
Hmm.
because of that, it will attain a new equilibrium after some time where you will want to reduce the N2 a little bit,
Yeah.
and because
mm,
N2 is reduced, H2 is reduced by double that amount,
Yeah. Yeah.
triple that amount, N2 plus 3H2, right?
Yeah.
yeah,
Triple.
yeah,
So the reduction in H2 is triple, the red line is falling sharply, right?
Yeah.
And the N2
And
NH3 is
NH3 is doubled.
increased by double, right?
Yeah. Yeah.
And
yeah, yeah,
eventually after some time a blue equilibrium phase has been reached now, right?
Yeah.
But notice that in this new equilibrium phase the concentrations of H2 and NH3 and N2 are all different from the initial equilibrium phase, right?
Yeah. Yeah.
You understand, initial equilibrium was at 3, 2, and 1. New equilibrium is at different values, no?
Yeah.
So basically, changing the concentration of any one of the reactants or products will help you attain a new equilibrium state where the equilibrium concentrations will be different now, right?
Different. Yeah.
Right? But the K constant remains the same, obviously,
Same. Hmm.
because you are not changing temperature or anything, right?
Yeah. Yeah.
Is this clear?
Yeah.
yeah,
So the concentration stress of an added reactant or product is relieved by net reaction in the direction that consumes the added substance, right?
Yeah. Yeah.
Concentration stress of a removed reactant or product, right, is relieved by net reaction in the direction that replenishes the removed substance, right?
yeah,
If
Yeah.
you remove something, then reaction will happen in the direction that brings that something back, right?
Back. Yeah.
So this is why, for example, you can take an example here and see that if you keep water in a glass and cover it up, right,
Hmm.
then that water will remain there for months and years and all. Okay,
Hmm.
like
yeah,
you can keep a water in a glass and cover it up, and that water will remain there forever. Okay,
Yeah. Yeah.
because what is happening is in this space, water vapor is there, right?
Yeah.
And the equilibrium has been reached where water is evaporating and this vapor is condensing,
Coming back. Yeah.
right? So this equilibrium
yeah,
is going to be maintained here, right?
Yeah.
And since there is no escape, eventually concentrations will be fixed and that is how it will be, right?
Yeah. Yeah.
However,
yeah, yeah,
if you open this thing, right,
Hmm.
eventually after some time it will go away, all the water will evaporate.
Yeah.
Why? Because when you evaporate it can escape,
Yeah.
right? So technically what is happening is, and especially if there is a wind or something, right, if there is a fan, right, you are letting it escape easily, right?
Yeah.
So you are removing the portion of the equilibrium that the product of the equilibrium has been removed, no?
Yeah. Yeah.
Like water liquid was becoming water
Water
vapor,
gas. Yeah.
right? And you are removing this from the reaction mixture, right?
Yeah.
If you are removing this, the reaction will proceed in such a way to replenish this, right?
Yeah.
yeah,
It
yeah,
will be replenished if the forward reaction keeps happening, right?
Hmm.
So more and more keeps coming in to replace the H2 that is gone, right?
Yeah. Yeah.
H2O that is gone, right? And that is why eventually the whole glass bottle will be evaporating,
Yeah. Yeah.
right? The whole water will evaporate eventually because the product is constantly being taken away, right?
Yeah. Yeah.
Right. So that is
yeah,
the idea here. It's fairly simple. Uh, so
Hmm.
then he's saying, let's go down a little bit. He's calculating the values now. So for the initial equilibrium mixture of 0.5 molar NN2, 3 molar H2, and 1.898 molar NH3, QC equals Kc because the system is at equilibrium. Okay.
Yeah.
Initially it was at equilibrium, so QC, he did the calculation, it comes out to be same as Kc, right? When we
Yeah.
disturb the equilibrium by increasing N2, you have suddenly made Q become smaller, no?
Yeah. Yeah.
If you added a reactant and tripled the amount of N2, you have made Q one third of the
One.
original Q,
Hmm.
0.29, no?
Yeah.
Yeah, yeah,
So for the reaction to move to a new state of equilibrium, QC must increase, right?
Increase. Yeah.
And that can only happen if numerator increases with respect to the denominator, right?
Yeah.
So NH3 has to increase, right? NH3 concentration, right?
Yeah. Yeah.
And N2 and 3H2 must fall, right?
Founder. Yeah.
So that is what happens finally. When the new equilibrium is established, the concentrations are 1.31 for N2, 2.43 for H2, and 2.36 for NH3, right?
Hmm. Yeah.
And again, you attain the same 0.29 value of the Kc, right?
Yeah. Yeah.
So this is this. Uh, as another example of how a change in concentration, let's consider that he is making one more example. Uh, in this example, what is important here is he's saying shifts in the position of this equilibrium can be detected by observing how the color of the solution changes when we add various reagents. Okay.
Hmm.
If we add aqueous FeCl3, right? So aqueous FeCl3 will provide Fe3 plus, right?
Yeah. Yeah.
If you add FeCl3 to the reaction, right, you are basically sending more Fe3 plus ions, right?
Yeah.
yeah,
If you're sending more of the ions of the reactant, then forward reaction will be favored, no?
Favored. Yeah.
And so forward reaction will happen more. So red color will appear more, right?
Yeah. Yeah.
yeah,
The
yeah,
red color will get darker, right?
Hmm.
However, if you somehow add FeNCS, right?
Yeah.
So that will also actually favor the forward reaction only.
Yeah. Yeah.
The equilibrium can be shifted in the opposite direction by adding reagents that remove Fe3 plus or SCN minus, right?
mm-hmm,
Yeah. Yeah.
For
That's.
example, oxalic acid H2C2O4, a poisonous substance present in leaves, okay, whatever, reacts with Fe3 plus to form a stable yellow complex, right?
Hmm. Hmm.
Thus decreasing the concentration of Fe3 plus, right?
Yeah.
So,
Yeah.
so oxalic acid basically decreases the concentration of Fe3 plus, right?
Yeah.
So now that will in if you add oxalic acid, then that will reduce the concentration of Fe3 plus and bring the backward reaction to
Hmm.
happen, make it happen, right?
Yeah.
So the red color will get down and the pale yellow color will start appearing, right?
Yeah. Yeah.
Right. So
yeah,
red color will disappear basically.
Yeah.
Okay, so this is clear. Then we move on to 13.8 reactions altering an equilibrium mixture by change in pressure and volume, right?
Mm-hmm.
So change in pressure and volume again is what we discussed earlier. In
Yeah.
general, it predicts that increase in pressure by reducing the volume will bring about net reaction in the direction that decreases the number of moles of gas, right?
yeah,
Yeah.
yeah,
So if you increase the pressure by say reducing the volume, right?
Hmm.
Then what will happen is the reaction wants to increase the pressure again, right?
Yeah.
No,
Yeah.
decrease the pressure because you
Decrease the
have
pressure.
increased the pressure.
decrease.
So how will pressure will decrease for the reactant mixture? It will happen
Go to
if you
the
go to the side which has less
less
moles of
gas.
gas,
Yeah.
right? Okay. A decrease in pressure by expanding the volume of a gas, expand the volume and thus decrease the pressure, will lead to net reaction in the direction that increases the number of moles of gas, right?
Yeah.
Again, obvious, right?
Yeah.
It's
Yeah.
again the same principle. So so that is what he will explain for the again ammonia reaction, right?
Hmm.
So QC initial was at equilibrium, and how he is doing what he is doing, disturbing the equilibrium by reducing the volume by a factor of 2, right?
Yeah. Yeah.
So reducing the volume by a factor of 2 means you are increasing the concentration, right?
Yeah.
Correct. We not only double the total pressure, we also double the partial pressure and thus the
Yeah.
molar concentration of each reactant, right?
Yeah.
Because
Yeah.
molarity is equal to N by V, right? Number of
Hmm.
moles by volume. And N by V is P by RT, right?
Yeah.
Correct. So if you are doubling the pressure, right? You are doubling the molarity also, right?
Hmm. Yeah.
At the same temperature, if you are doubling pressure, right? You are basically
Hmm.
doubling molarity also, correct?
Yeah. Yeah.
Yeah. Yeah.
So, because the balanced equation has more moles of gaseous reactants than gaseous products, the if the molarity is doubled for each, right?
Hmm.
So
Hmm.
notice that the Q uh, on top it is 2 square and on the denominator is 2 power 4, right?
Yeah. Yeah.
So you have technically reduced the Q, no? You have reduced the
Yeah.
Q by a
Reduce the
huge
Q.
4 factor, right?
Hmm.
Hmm.
So then
Yeah.
the
Yeah.
reaction should proceed in forward direction, no? Then
Yeah.
is it making sense, everyone?
Yeah.
Yeah.
Right. So for the so he has found the new Q. New Q became 0.0726, okay, which is four
Hmm.
times less than the original one, right?
Yeah.
And for the reaction to move to a new state of equilibrium, QC must increase, which means that net reaction goes from reactant to product, as predicted by
Yeah.
Le Chatelier's principle, right?
Hmm. Yeah.
So in practice, the yield of ammonia in the Haber process is increased by running the reaction at high pressures, typically 130 to 300 atm.
Yeah.
Right?
Yeah.
Okay. The composition of an equilibrium mixture is unaffected by a change in pressure if the reaction involves no change in the number of moles of the gas, right?
Hmm.
Now, for
Yeah.
example, if you tried the same to the reaction H2 plus I2 gives 2HI, right?
Hmm.
Then actually the moles of gas remain same here, no?
Same. Yeah.
So nothing, you cannot change the composition of the equilibrium mixture by changing the pressure or volume of this reaction,
Hmm. Hmm.
right? It will only happen when delta N is not zero, right?
Yeah. Yeah.
Then only you can use this pressure and volume trick to change the equilibrium mixture composition, right?
Yeah. Yeah.
Yeah.
Because here both denominator and numerator factors will cancel out, no? So increasing pressure and volume will doesn't change the concentration at all.
Yeah. Yeah.
Q doesn't change, no?
Hmm.
Is it clear why Q doesn't change?
Yeah. Yeah.
Yeah.
Got it.
Okay. So applying Lee Chatelier's principle to pressure and volume changes. So for example, let's look at this example 13.13. He's saying, does the number of moles of reaction products increase, decrease, or remain the same when each of the following equilibria is subjected to a decrease in pressure by increasing the volume, right?
Hmm.
Okay, so number of moles of products we have to say, right? So
Yeah.
Yeah.
ECl5 gas, you are decreasing the pressure by increasing the volume, right?
Yeah.
So
Yeah.
decreasing
Yeah.
the pressure means your reaction should go towards the side that increases the pressure.
Increases pressure. Yeah.
So
Some
that
more
will be
gas.
towards forward direction, right?
Yeah.
So
Hmm.
more, it will increase, right? Product concentration should increase, right?
Yeah.
Yeah.
In the first part. In the second one, uh, you have to again increase the pressure. So backward reaction will be favored
Yeah.
Yeah.
because
Backward.
forward is a
Backward.
solid and there is backward gas one, right?
Yeah.
Yeah.
In the third one, 4H2, 4H2, nothing will change, right?
Nothing. Yeah.
Yeah.
It will
It's the
remain
same.
same, no? Because the
Yeah.
amount of gases on both sides are same.
Same. Yeah.
Hmm.
Okay, so this is clear. Now we'll look at change in temperature as a factor, right?
Yeah. Yeah.
13.9. So when an equilibrium is disturbed by change in concentration, pressure, or volume, the composition of the equilibrium mixture changes because the reaction quotient QC no longer equals the equilibrium constant Kc, right?
Hmm.
This is
Hmm.
what we have been seeing earlier, no?
Yeah.
Yeah.
As long as the temperature remains constant, however, concentration, pressure, and volume changes don't change the value of the Kc, right?
Yeah. Yeah.
So Kc has remained fixed throughout what we have done earlier, right?
Yeah. Yeah.
You are changing
Yeah.
one of the values of the reactant concentration or reducing concentrations throughout or increasing concentrations throughout by changing pressure or volume, right?
Yeah. Yeah.
By contrast, but you had not changed the K value at all. You were changing Q values and saying that because of new Qs, now reaction will go further in one direction or the other, right?
Yeah, yeah.
Now, in this case, you are going to change the temperature, and
Temperature.
that nearly always changes the value of the K itself, right?
Yeah, yeah.
So, for the Haber synthesis of ammonia, which is an exothermic reaction, the equilibrium constant Kc decreases by a factor of 10 power 11 over the temperature range 300 to 1000 Kelvin. So basically,
Mm.
he's saying that N2 plus 3H2, right now it is exothermic with minus 92.2 kilojoules, right?
Yeah.
At low
Yeah.
temperatures, the equilibrium mixture is rich in NH3 because Kc is large, right?
Yeah.
See, at low temperatures, like here it is, this K value has been plotted versus temperature, okay? So
Yeah.
as the temperature increases, you see that K value is decreasing, right?
Mm-hmm.
So the scale is logarithmic, okay? So it looks like it is a normal minor decrease, but it's actually a huge decrease.
Yeah, yeah.
Okay, Kc is plotted on a log Kc has been plotted basically there. Okay.
Mm-hmm. Yeah.
And this side it is temperature is being increased, fine.
Increased. Yeah.
So so if Kc is high in the beginning, then that means NH3 was high, right?
Yeah.
At low temperatures, right?
Yeah, yeah.
But as you go to high temperatures, uh, NH3 will be lower then,
Lower, yeah.
right? So
Yeah.
in general, the temperature dependence of an equilibrium mixture, equilibrium constant, depends on the sign of delta H for the reaction, right?
Yeah.
Sign of the enthalpy change for the reaction.
Yeah,
And
yeah.
it is in the same way that we thought earlier, that enthalpy change decides whether a reaction is endothermic or exothermic, right?
Exothermic, yeah.
So if you change the temperature, the reaction should relieve that stress, right? So
Yeah,
if I
yeah.
decrease temperature, reaction should try to increase temperature, right? And
Yeah.
Yeah.
reaction will try to increase temperature by going in the exothermic direction,
Yeah.
right?
Hmm.
And
Yeah,
reaction
yeah.
will try to
Yeah.
reduce the temperature by going in the
Going in
endothermic
endothermic, yeah.
direction, right? So he's saying the equilibrium constant for an exothermic reaction decreases as the temperature increases. That means temperature, if you increase, it will go backward, right? Reaction should go backward for an exothermic reaction, no?
Yeah.
The
Yeah.
endothermic direction is backward, no?
Yeah, yeah.
So if the reaction goes backward, then product concentrations are falling, right? So the
Hmm.
K value should reduce, no?
Yeah, that's correct.
Makes sense because K value has product by constant by reactants, right? So
Yeah.
if the
Yeah.
reaction goes backward, reactants are becoming more, products are becoming less.
Less.
So equilibrium constant itself should decrease.
Yeah.
And if equilibrium constant for an endothermic reaction, it increases as temperature increases, right?
Yeah, yeah.
So again, he's explaining that using Lee Chatelier, he's saying if heat is added to an equilibrium mixture, thus increasing its temperature, net
Mm.
reaction occurs in the direction that relieves the stress
Relieve stress. Yeah.
of the added heat. For an endothermic reaction such as decomposition of N2O4 and all, heat is
Mm.
absorbed by the reaction in the forward direction.
Yeah.
Yeah.
Basically, endothermic in the forward direction. So equilibrium therefore shifts to the product side at higher
Product
temperatures, right?
side, yeah. Mm.
So
Yeah.
higher temperature, endothermic reaction K will increase. Okay.
Yeah, yeah.
Temperature increases, endothermic reaction K
K
increases,
increases.
exothermic reaction K decreases. Right?
Yeah, yeah.
But if you are confused, think about it in terms of Lee Chatelier's principle.
Hmm.
How will you reduce the temperature or increase the temperature? You will go towards either exothermic side if you want to increase and endothermic side if you want to
Endothermic,
decrease.
yeah.
Right?
Yeah.
Yeah.
And that itself will tell you whether K should increase or decrease. Right?
Yeah, yeah.
Okay. So this is fine. Then effect of a catalyst also we have discussed. Effect of a
Yeah.
catalyst he is explaining here that there is an uncatalyzed pathway and then there is a catalyzed pathway, right?
Mm-hmm.
So if there is an uncatalyzed pathway, the activation energy was higher, right?
Yeah,
But
yeah.
if you
Yeah,
look,
yeah,
look at it, the reverse activation energy was also high, right?
Mm-hmm. Yeah,
Backward
yeah,
reactions
yeah.
activation energy was also high. And when there is a catalyzed pathway, the both the activation energies are reduced by the same amount,
reduced. Yeah.
right?
Yeah, yeah.
So rates of the forward and the reverse reactions increase by the same factor
Yeah,
if you go
yeah,
in a catalysis type of situation, right?
yeah.
And now, because both rates have increased, reaction will reach equilibrium faster, but the
Faster.
concentration remains the same,
Same.
right?
Yeah.
Yeah, yeah.
So so he's saying in the paragraph below, he's saying even though a catalyst does not change the position of an equilibrium, it can nonetheless significantly influence the choice of optimum conditions for a reaction.
Yeah,
Look
yeah.
again at the Haber synthesis of ammonia. Because the reaction is exothermic, its equilibrium constant decreases with increasing temperature, right? And
Yeah,
optimum yields
Yeah,
of NH3 are obtained at low temperatures, right?
yeah, yeah.
At those low temperatures, however, the rate at which equilibrium is reached is too
Is
slow for the
low.
reaction to be practical. Okay.
Yeah, yeah.
We thus have what appears to be a no-win situation. Low
Mm-hmm.
temperature gives good yield but slow rate,
Snow
right?
rate. Yeah,
Whereas high temperature gives satisfactory rates but poor yields, right?
yeah, yeah.
The answer
yeah.
to the dilemma is to find a catalyst, right?
Catalyst. Yeah.
In the early 1900s, Fritz Haber discovered that a catalyst consisting of iron mixed with certain metal oxides causes the reaction to occur at a satisfactory rate at temperatures where the equilibrium concentration is reasonably favorable, right, for
Mm.
ammonia.
Yeah.
So basically, he's saying yield of NH3 is reasonably favorable at
Favor.
some 400, 500 degrees centigrade, where because of catalyst, the rate is also fast, right?
Yeah, yeah.
Yeah, yeah.
So you understand the choices, right?
Yeah, yeah.
Okay. Uh, so catalyst basically will help you increase the rate at which the equilibrium is reached, right?
Yeah.
Now he will come to this 13.11, which is the link between equilibrium, chemical equilibrium and chemical kinetics, right?
Mm-hmm.
So he is looking at this reaction. A plus B gives C plus D, right?
Yeah.
Reversible reaction. Let's assume that forward and reverse reactions occur in a single bimolecular step. These are elementary reactions, okay?
Yeah.
We had seen earlier that actually any complicated reaction will not happen in a single step, right?
Yeah.
And in chemical kinetics, we know that it could happen in multiple steps where the most important step would be the rate determining step, which is the slowest step in that
Slowest.
reaction,
Yeah.
right? And
Yeah,
order of the reaction you have to figure out from the rate determining steps order, right?
Yeah. Yeah.
Correct. So the number of
hmm.
molecules, each elementary step you can figure out the order by just looking at how many molecules are colliding, right?
Yeah. Yeah.
Overall reaction order you cannot figure out by just looking at the reaction coefficients and all, right?
Mm-hmm.
Only if it is an elementary reaction
And
can we know the order of the reaction and all, right?
yeah. Yeah.
Right. So he's assuming here for the purpose of this derivation that these are both elementary reactions, okay? A
Hmm.
plus B gives C plus D, and basically reverse reaction is C plus D
So
gives equilibrium,
yeah. Yeah.
right? And
Yeah,
we can then write the following rate laws. Rate forward is equal to Kf AB, rate
Yeah.
reverse is equal to Kr CD, right?
Mm-hmm.
So if we begin with a mixture that contains all reactants and no products, initial rate of reverse reaction is zero, and initial this we have already discussed. Finally, both the rates will become equal, right?
Yeah.
And KFAB is equal to KRCD, right?
KRCD.
So
Yeah.
KF by KR will be CD by AB, right? And
Yeah.
this is what is
yeah,
called
yeah.
as KC.
Yeah.
So therefore, the equilibrium constant is simply the ratio of the rate constants for forward and reverse reactions, right?
Yeah. Yeah.
In deriving this equation for Kc, we have assumed a single step mechanism, right?
Yeah.
For a multi-step mechanism, each step has a characteristic rate constant, right? Each
Yeah.
step
Yeah.
will have its own Kf by Kr, Kf by Kr, right?
Yeah.
When
Yeah,
the equilibrium is reached, each step in the mechanism must be at equilibrium, right?
Okay.
and
yeah,
Kc for the overall reaction is equal to the product of the Kc for each of the individual reactions, right?
Yeah.
So Kf by Kr 1 into Kf by Kr 2 into Kf by Kr 3 is the Kc overall.
Yeah.
Okay.
Yeah.
yeah,
The equation relating Kc to Kf and Kr provides a fundamental link between chemical equilibrium and chemical kinetics. The
Mm.
relative values of the rate constants for forward and reverse reactions determine the composition of the equilibrium mixture, right?
Yeah. Yeah.
When Kf is much larger than Kr, Kc is very large and the reaction goes almost to completion.
Mm.
Such a reaction is sometimes said to be irreversible because the reverse reaction is often too slow to be
Too
detected.
slow. Yeah.
When Kf and Kr have comparable values, Kc has a value near 1 and comparable concentrations of both reactants and products are present at equilibrium, right?
Yeah.
This
Yeah.
is the
yeah,
usual situation for a reversible reaction, right?
Mm. Yeah.
Addition of a catalyst to a reaction mixture increases both rate constants because the reaction takes place by a different lower energy mechanism. Because
Yeah. Yeah.
Kf and Kr increase by the same factor, though the ratio is unaffected and the value of the Kc remains unchanged, right?
Unchanged. Yeah.
So recall the equation Kc is equal to Kf by Kr also explains why equilibrium constants depend on temperature. You have the
Mm.
Arrhenius equation, no? K is equal to AE power minus
Yeah.
EA by
Yeah.
RT, right?
Yeah.
In general, forward and reverse reactions have different values of activation energy, right?
Yeah.
Because notice that they will have same value of activation energy only if both the products and reactants are at the same energy level.
Same energy. Yeah.
In general, you will have something like this, right?
Yeah.
The forward reaction activation energy will be EA and the backward reaction will be something higher, no? EA
Yeah.
plus
yeah,
delta H or something, right?
Yeah. Yeah.
Right. So clearly, if you change the temperature, Kf uh, dash will be, okay, 1 second. So generally the reaction will be written like this: Kf is equal to A e power minus EA by RT, right?
Yeah. Yeah.
How Kb will be A e power minus EA plus del H by RT, right?
Yeah. Yeah.
And if you change the temperature, this change is going to be different from this change, no?
Yeah. Yeah.
Because the factor on top of the exponentiation is different, no?
Different.
yeah, yeah,
Correct. So the effect of changing temperature is not going to be balanced, right?
Yeah.
Forward
Not.
reaction will change by a different amount and backward reaction will change by a different amount, right?
Yeah. Yeah.
yeah,
So therefore the K will definitely change then, right?
Yeah.
If you change the temperature, the rate effect is not equal, right?
Yeah.
yeah,
You understand?
Yeah. Yeah.
So therefore, you get a different value of the K now, and therefore we have the Lee Chatelier's principle for what happens when temperature changes, right? And
Mm.
you notice now that this dependence clearly depends on the value of delta H, right?
Delta H. Yeah.
yeah,
If delta H is positive, it will be different, and if it is negative, it will be different, right?
Yeah.
yeah,
Yeah.
So the reactions will behave differently for exothermic and endothermic situations,
Yeah. Yeah.
right?
yeah,
Okay. So this is so this is the end of the chapter now. The chapter is over. Now you have to do the exercises.
Mm.
What is the situation in Alan? Have they finished the chapter?
No, they haven't finished. I'm still doing.
Okay, okay. Uh, they haven't finished. They are doing it right now.
Yeah. Yeah.
yeah,
Okay, so you should also try the exercises at the end of this chapter.
Yeah. Yeah.
If you can find out, tell me what they are planning. Are they going to do ionic equilibrium and all right now after this?
I don't know. We finished the Chatelier now, and after that we just started doing questions.
Okay, so questions is fine, but next chapter in your chemistry booklet is what?
Second.
Like we have to decide what we are going to do.
in our unit book, it's S block and hydrogen.
S block and hydrogen. That has already been
Yeah,
done or not? No.
no, no.
And after that, do you have any other chemistry books after that?
Yeah, there's one more.
So just check the chapters in that.
It's GOC structural and
Okay, fine. So they are not doing
conformational
ionic equilibrium. They will start
acids.
Yeah, it's
organic.
organic.
Yeah,
So we will also start organic chemistry then.
Hmm.
Okay. So they are not going to do ionic equilibrium right now. They will do ionic equilibrium next year.
Okay.
So the next chapter for us is chapter 14 is acids and bases, and in the McMurray book, and then chapter 15 is ionic equilibrium. Okay. So these chapters actually we can also postpone, and we will do it as and when required. Acids and bases is actually a useful chapter for organic also. So maybe we'll see, but I will plan on starting organic then. Okay,
Yeah, okay.
okay.
because that is the most difficult part of chemistry in 11th and 12th.
The ionic equilibrium is actually part of that chapter. So
Ionic
might we
equilibrium
will
is
be
actually
doing
part of which chapter?
equilibrium itself. Yeah, there's a part B. It's ionic equilibrium.
Is it written ionic equilibrium and all in your equilibrium chapter only?
Yeah.
Uh, just check if there is something like KSP or Ka for acids, and is there something like that in the chapter sections? If you have the PDF, if you can send it to me, I will be able to see. Is there things called
There's
solubility product, Ka,
there's some
Kb?
dilution law and all.
Then after that, what is?
Then then it's pH for something. pH is acid is strong.
pH is there, no?
Yeah.
And
Yeah,
then
yeah,
okay, so then I think they are doing acids and bases and everything.
Yeah. Yeah.
Is
Buffer
there KSP?
solution.
yeah,
Buffer solution.
Buffer
Then
solution and all is there. Then after that, go till the end of the chapter.
acid
Tell me.
base titration
Uh,
indicators. Then
yeah.
yeah,
KSP
KSP
is
is
the
the solubility and solubility product.
oh,
solubility
okay.
product.
Then they are doing everything basically.
Hmm.
Then we have to do 14 and 15. Okay.
Yeah.
And after that, we'll start this.
Yeah. Yeah.
Yeah, yeah,
Fine. So, fine then. We'll go till chapter 15 then. And then when they do S block and all, before that, we'll start organic.
Yeah.
So, S block and hydrogen and all will be super easy, and you guys will be able to figure out it yourself. There is nothing very difficult there. You have to read NCRT book, you have to learn some facts. Okay.
Okay. Okay.
NCRT and Allen book will be fine for now. Eventually, you should read some nice textbook like J.D. Lee, but J.D. Lee, there is a book called Concise Inorganic Chemistry. Okay,
Mm-hmm. Mm-hmm.
if some of you may have it, this is very good.
Yeah.
Inorganic Chemistry by J.D. Lee. You should have it, or online version you can find it. It will be available somewhere. PDF
Mm-hmm.
you can find.
Mm-hmm.
yeah,
Uh, Inorganic right now we are not focusing on so much because most of the people can figure it out themselves. It's not very hard.
Mm-hmm.
Uh, After we do 14 and 15, we will go to organic. Okay. And
Yeah.
organic, I will tell you the textbook. You should buy one textbook at least. So it will either be Paula Bruce, or it will be Clayden. So one
Okay.
of these two, I will take a call and I will decide and tell you. So you
Yeah.
should buy one of them,
yeah,
and we'll be using that textbook for learning this subject. Okay.
Yeah. Yeah.
yeah,
Uh, yeah, for now that is it. Then we what we'll do this Thursday, we will start the acids and bases part. uh,
Mm-hmm.
you should do the problems and all that you are supposed to do in
Yeah.
the
Yeah.
class, and whatever is the exercise of chapter 13. It is not very difficult so far. So
Mm-hmm.
acids and bases and ionic equilibrium will be slightly more difficult, not very difficult, but
Mm-hmm.
slightly more involved. So we'll see that.
yeah.
Okay.
Yeah. Okay.
Okay, that's it for now.
Mm, yeah.
Bye.
That's all.
Bye, sir.
Mm.